all the way back to the next highway. And the question might come up is, why do we have such a large land area when the towers don't even have guy wires? They just kind of stand there, and you'd wonder what all of the ground is sitting out here doing. Well, the answer to that is that with AM towers, you have what are called ground radials, which are buried in the ground. And a radial, by its very nature, starts at the center, which means starts at the base of the tower, and is a number wire, probably, I think, about a number 8 or number 10 gauge wire, copper wire, that's plowed into the ground when the tower is built. And there are 120 of them, spaced 3 degrees apart, all the way around the tower, plowed in at a depth of about 4 to 6 inches, at a distance equal to a quarter wave at the frequency that we're talking about. So our frequency is 680, and a quarter wave at 680 is about 370 feet or so. So virtually all AM stations are built this way with these ground radials. The ground radial system in antenna terms is called a counterpoise. It is actually half of the antenna. As you know, from a simple dipole antenna, you in essence have a feeder. You either have a balanced or an unbalanced feeder line, but you've got in essence 2 conductors, a ground and a hot lead. And then you've got 2 leads on a dipole. Well, when you turn the dipole vertically, what we end up having is half of the dipole above the ground and half of it below the ground. And the half below the ground is the ground radials. And so they're in the ground, and each of these 3 towers has a ground radial system that was put in the ground when the tower was put up. We have to be careful whenever we do any digging around this building, because if we go down 6 inches, there's no electrical shock danger at all, because the ground radials are at ground potential and they're buried, but there is RF current flowing through those ground radials, and if we cut 1 or 2 or 3 of them, no big deal, but if over a long period of time we cut a large number of them, the efficiency of the antenna system would drop. And I'm sure as long as these ground radials have been in the ground, there are probably some that are indeed cut, but we take every precaution whenever we have to dig to avoid them. For example, right about over here where you see this plastic pipe laying on this side of the building, we had an old fuel storage tank that we had to have removed about 6 months ago because it had been abandoned. You know, EPA has got all these regulations about removing abandoned storage tanks. Well, when we started digging up the tank and digging around it, sure enough, there were ground radials buried there, about 6 inches below the surface. So we continued operating. There's no problem with continuing to leave the station on the air while the ground radials are disturbed. We had to cut the ground radials to get them out of the way. That's no problem. We did that, stayed on the air. Nobody noticed the difference. The thing is that after we were done and all the dirt was put back in the hole, we had to take those ground radials and silver solder them back together to reestablish the integrity of the ground system. Since there are 120 of them around the base of each tower, anything you do to any 1 or 2 is going to have negligible effect. The problem is we want to maintain the integrity of the system as a whole, and the only way to do that is to be meticulous about every ground radial so that you don't deteriorate the system over a period of time. When we get inside the building, you'll see a diagram of how those ground radials are laid out, but and they're not all a quarter wave, but generally that's the rule of thumb that's used, is that most AM antenna systems today have quarter wave ground radials, and then the other quarter wave is the tower itself. Now, unlike the FM and TV that we saw last week, where the tower is a supporting structure for the antenna, with AM, the tower is the antenna. Okay, the radiation, there is not, even though you see some other things up there that I'll explain later on, that has nothing to do with the AM station. The tower itself is the radiating element. And since we're talking about frequencies that are much, much lower than the frequencies we were talking about last week, the physical size of an antenna to a great extent is a function of the frequency and wavelength. So the lower the frequency you're talking about, the longer the wavelength. A wavelength at 600, one wavelength, for example, at 680 kilohertz is about 14 or 1500 feet for one wavelength. Now, a wavelength at say 94.7 at the FM band might be 120 inches. Okay, so you can see the difference, and that's just a simple matter of velocity equals frequency times wavelength. Do I have that right? Okay. And so as you increase the wavelength, you lower the frequency, etc., vice versa. The constant there, of course, is the velocity of the electromagnetic waves through the air. So what we have generally is a quarter wave above the ground. Now, the two shorter towers, and we'll explain why there are three towers here in a little bit, but the shorter towers are indeed a quarter wave. So they're about 370 feet each. This larger tower is longer than a quarter wave. It is closer to a half wave. The two shorter towers were put up here in about 1934. Well, let me put it this way. There were two short towers put up here. It wasn't those two, but they were on this property, and they were in the back of the property. In 1940, if I'm not mistaken, 1940, those two towers were put up. In 1948, this large tower was put up. Okay, now let me explain why we have a large tower, why we have three towers. On AM, and at generally all frequencies below about 30 megahertz, you've got, to varying degrees, a phenomenon called skywave, which is what enables you to hear shortwave stations around the world. On the AM broadcast band, the skywave is really only present at night after sunset, from sunset until sunrise the next morning. That enables you to hear AM radio stations hundreds or thousands of miles away. Well, that's good if your hobby is broadcast band DXing and you like to listen to stations far away, but it's a problem in trying to allocate AM broadcast stations all over the country, because one can interfere with the other if several stations are on 680 and you're on the outskirts of a particular station's coverage area and you're hearing too much of the station 1,000 miles away and not enough of the station that you want to hear. So early on, back in the 30s, the FCC decided that they would require AM stations at night to use directional antennas, which means that and a directional antenna works similar to what we were talking about last week in having multiple bays on the FMs to concentrate the signal. The problem is that on the FM, with the FM antennas we talked about last week, the spacing that is needed, because the wavelengths are so much shorter, all of that can be accomplished at the top of one tower, the spacing between the bays and so forth. Here, the wavelengths are so much longer that in order to get the kind of spacing that we need for the proper phase relationship to get the signal to go where we want it to go, we're talking about hundreds of feet apart. So the only way to do that, since the antenna itself is the radiating element, is with multiple towers. Instead of, in essence, it's a multi-element array, just like we had a multi-element array last week. Now, don't get me wrong, the purpose of these multi-element arrays in AM is different than the purpose in FM. The purpose in FM essentially was to keep the signal from going straight up where you really didn't need it, to keep it going out on the horizon. In AM, what we're trying to do is to protect stations at certain distance in certain directions. When WPTF went on the air in 1924, but when it went on 680, which was in the 30s, there was already a couple of other stations on 680. There was one in Boston, one in San Francisco, and probably a few others. So the FCC's rules were written in such a way that if you newly occupied a frequency, you had to protect at night after sunset the stations that were there first. So that meant that what we had to do was design a directional antenna pattern that at an azimuth of 37 degrees, by 37 degrees I'm talking about north being 0 degrees, okay? And south would be 180 degrees, and east is 90, and west is 270. So when I say an azimuth of 37 degrees, that means that when I point myself 37 degrees or do it with a compass, I'm looking toward what would turn out to be Boston, okay, which is where there was already a station on 680. So they said that they wanted us to restrict our radiation in the direction of Boston at night to a particular value which would be low enough that it wouldn't cause them any interference in that direction. Similarly, we had to protect San Francisco to a lesser extent, although the station in San Francisco kind of had almost squatters' rights on the frequency because of the fact that they were there first. So they were allowed to continue operating with 50,000 watts non-directional while we had to restrict our signal in their direction. So at that angle, which happens to be about 285 degrees, which is kind of west, they said, we want you to restrict your radiation in that direction. So the engineers at the time determined that by using a two-element directional antenna pattern with the two short towers, that we could protect those two stations at night, but they said you only need to do it at night. You don't need to do it during the day, because during the day your skywave AM signal is absorbed by the ionosphere and does not bounce back to the Earth, which is essentially what happens the way skywave works. Your signal bounces off the ionosphere. The atmosphere is ionized during the day by the sunlight and absorbs the radio signals at that frequency, whereas at night the ionization disappears and the signals are reflected back to Earth several hundred miles away. They're not reflected back to Earth at every point between here and that point several hundred miles away, but there's a random reflection going on, so you can hear it in some places, not hear it in others. And of course, as the atmosphere changes, the signal will fade, and if you're at any distance trying to listen to these stations, you'll hear them, and then 5 minutes later they're gone, and 5 minutes later they're back again. So that's essentially why we have a two-element directional antenna here. When I say a cardioid pattern, some of you may know what I mean. Essentially, it's like a cardioid would be like a small circle and a large circle, end to end, tangent to each other. Okay, and in fact, I'll show you a picture of it when we go inside. But essentially, what it does, it takes most of our signal, and it's like a balloon. When you pull the signal in, if you take a balloon and squeeze it at a certain point, it's going to bulge somewhere else. So we take our power, and we're not really losing any power when we do that. We're losing signal in those particular directions, but it makes the pattern bulge in another direction. So that means, like to the south and east, we actually put out more signal than would otherwise be the case if we were non-directional. Now, the maximum AM power that's allowed in the United States is 50,000 watts, which is what WPTF is. There are probably, I would say of the 4,000 AM stations in the country, there are probably less than 200 that are 50,000 watts. Most of them are 5,000 and 1,000. Because they were able to allocate more stations by having lower powers later on in the later years. The stations that were on early, like we were in the 20s and 30s, were the ones that were most likely ended up 50,000 watts because they kind of had their choice of frequencies and they were able to increase power before the other stations came around. Most of the AM station building occurred post-World War II, from about 1945 to about 1955. Most of the AMs were on the air, and the ones that were on before that generally have somewhat of an advantage. So we operate at 50,000 watts. There are various ways that AM stations protect each other. As the bands got more and more crowded, it became more and more difficult for a station to operate at night and still meet the FCC's criteria for protecting the stations that were already there. In our case, we only had to protect 2 stations. There are stations that came on the air in the 50s that were faced, because of the frequency that they chose, or for just the fact that there was no other choice, that maybe had to protect 6 or 7 stations. And in some cases it got to be a situation where they had to protect stations in so many different directions that they, in effect, couldn't be on the air at night. So that's where you end up with the concept of an AM daytimer. Those are AM stations that are only on during the day. They came on the scene rather late, and so as a result they'll operate from sunrise to sunset and then sign off. Well, now within the last 5 to 7 years, the FCC has even allowed daytimers to operate at night, but at extremely low powers, like 50 watts, 25 watts, 100 watts, so that they don't have to build these expensive real estate gobbling directional antenna systems, but can still be on at night and maybe serve a local area. They're still generally referred to as daytimers because they're not operating at full power at night. The other ways that the stations have dealt with the restrictions on nighttime radiation is by constructing antenna systems with more than 2 elements if they had to protect several stations. WKIX, for example, in 1983 and 84, I was involved in rebuilding and relocating the WKIX antenna system, which used to be right out here at where I-40 crosses 54, and right about the time that I-40 opened, the owners of WKIX sold that property to some developers and rebuilt their antenna system, which I was involved in, out near Morrisville. And they put up 5 towers because of the number of stations that they had to protect. There are other ways that stations have dealt with protecting each other, or by reducing power at night. A station might be 10,000 watts during the day and 5,000 watts at night, which is what WKIX is. They may be 10,000 day, 5,000 night, and a directional antenna at night. So through the various combinations of reducing power and using directional antennas, that's why frequently you can be listening to an AM station around sunset, and all of a sudden, like, it goes away. It either goes away or it becomes real weak, and you don't understand what happened. You're just driving along, and all of a sudden that's what happens. Well, that's what happens, because right around sunset is when they'll switch. Now, there are some stations that even use a directional antenna system during the day, probably maybe less than 25% of them, and that's because they just happen to be too close to another station on that same frequency. They actually have to protect the other station even during the day. That has nothing to do with skywave. That's the simple ground wave signal. Is just too close to another station on the same frequency. There are stations that are that way, but they're generally in the minority. There are stations that use a directional antenna during the day and then use a different directional antenna at night and at a different power. So, and that usually involves quite a bit of real estate because the requirements. WDNC does that, right. Now, as to why we have 3 towers, now that kind of explains those 2. From 1940 until 1948, they operated with those 2 towers. When they're operating non-directionally, which would be during the day, there's only 1 tower in use. The other tower is detuned, which means it's not being fed at all. And in essence, the signal is being radiated in more or less a circle. Non-directional operation during the day. So that's what they did. They used this what we call the South Tower, which is the nearer one to us, during the day, and then at night, through some switching inside, we used both towers. In 1948, the Durham Life Broadcasting at that time decided they wanted to put an FM on the air. FM was just beginning back in the late 40s, post-World War II. Of course, with FM, as we talked about last week, you need some height, because the higher you are, the further out you get. Well, nowadays, the ultimate FM installation is something that's 1,600 or 2,000 feet, like we saw last week. Back in the late 40s, 500 feet was considered to be, a great accomplishment in structural engineering and an FM cover. So what they decided to do was to combine the AM and the FM, the AM daytime operation, and the FM into one tower, which means that we build a taller AM tower here, and we mount the FM antenna up on top of it. We have a combined AM and FM antenna. It's a combined structure. I don't want to say it's a combined antenna because that's actually a misnomer for me to say that, because remember, the tower is the antenna for the AM station, whereas the antenna which is mounted on the tower is the antenna for the FM. So it would be incorrect to be misled into thinking that they're actually being fed. Use elements like we talked about last week and much older design, but the FM antenna is you can see 1, 2, 3, there are actually 4 sections up there. You can see the white and the part of the red there that make up the FM antenna. The transmission line which feeds the FM antenna goes up the center of the tower, and there are several cables going up the FM antenna, several cables going up the center of the tower which do other things, but the biggest one out there is the FM line. Now, the pole on top of the FM antenna was a vision that they had back in the late 40s that they were also going to get a TV license. They were fighting with another company in town here to try and get a license for Channel 5. And Durham Light felt that with their track record in having the AM and the FM station here for so many years, that they were pretty confident that they were going to get Channel 5. Moved off of this site and moved out to the tower out at Apex. And then only within the last 2 years, we talked about last week, we actually moved WQDR out to Auburn. This, what you see here, is the transmission line which used to feed the FM antenna up the top. That transmission line is no longer usable. It's abandoned. It hasn't been used in 15 years or so. But leave at this site. This is the old Channel 28 antenna that was on the tower, and remember I said last week that the Channel 28 antenna is below the Channel 5 antenna because they're stacked. This is the heavier of the two. It's called a slot antenna, and you can see why it's called a slot antenna. It's got slots on the side. These slots are, and the elements inside them are a function, again, of the wavelength at UHF.
Same thing last week on the
AM frequencies are generally harmless. However, the federal government came up with standards several years ago whereby they don't want people to be exposed to RF energy depending on the frequency for certain distances. You can't be closer than that for a particular period of time. So generally you can be in here for 6 minutes, but there's a 6-minute exposure limit. So if you feel that for some reason you're worried about the radiation, then you don't have to come in. But it's non-ionizing radiation, essentially, is what it is. So the fact that if you look at where the tower rests on the pylon, it's actually resting on a porcelain insulator, which means that there is no metallic contact between the base of the tower and the anchor point. It is resting on a piece of porcelain, okay, which is kind of incredible when you see this much steel up there and it's all resting on 4 pieces of porcelain. Porcelain insulators are designed in such a way that they have incredible amount of energy under compression, but they're very, very poor on expansion. In other words,
is it very dense, or is that what you're saying?
Well, it's, porcelain is like what China's made of. It's designed in such a way that it'll hold well under compression. I don't know.
How much stress does it? Is it taking the weight of the tower?
It's taking the whole weight of the tower. The whole weight of the tower is being divided on in 4, because there are 4 of those insulators, one at each base. Okay, one at each of the 4 corners. All right. So there is no. The tower is not at ground potential, unlike the tower last week, which has all kinds of grounds on it. This tower is not at ground potential. Now, the transmission lines that are running up the middle kind of spoil that a little bit, but I'll explain that a little bit later, if at all, because that's a little bit of black magic that I don't really want to get. As they say in class, it's beyond the scope of this course. But the other two towers are true floating towers, which means that there's no connection whatsoever between the tower and ground other than what's feeding. Needless to say, the radials are denser closer to the tower than they are further out, because they tend to spread out as they go out. So
it's kind of interesting. I can hear the radio station to my camera.
Yeah, you probably will. As a matter of fact,
we'll see the video on that tape.
Yeah, I don't remember if it was here or the other side. I was out with my camera doing one, and I was getting a bunch of interference.
Yeah, fuzz through the.
Yeah, you're getting RF interference because those cameras weren't designed to work tower is hot. Now, when we have to climb the tower for maintenance, light bulb change, that sort of thing, it can be done with the tower on. And the way that we do that is we have a ladder that we'll put up to that platform. You can see there's a ladder that goes up the side of the tower. We have, in fact, the ladder's back there. It's a fiberglass ladder, but it's insulated. So as long as you don't have your feet on the ground at the time that you touch the tower, you can be on the tower, and the tower is at a high RF potential, but you don't feel anything because your whole body is at the same potential. It's only when you get across different potentials that you can actually get an electrical shock. Now, because of the FCC and new ANSI standards on RF exposure, there are limitations on at what power level that can be done. All I'm saying is in the days prior to these new regulations, and even now, it is possible to actually climb. The capacitors are designed to match this 50 ohm antenna impedance into the impedance of the tower, which happens to be about 122 ohms. So in essence, this is a matching network, is what we call it. In fact, it's you'll really get interference here on those cameras, I suspect. Okay. But that's the purpose of this network, is to essentially to match impedances for the maximum transfer of energy between the transmission line and the tower. And we go out that bulb insulator up there, up on the ceiling. Of course, at that point, then that connects to the legs of the tower above the building, which you'll see when you go outside, which feeds the antenna. This meter over here measures the current, and about 20 amps of RF current, and we can calculate the power based on that current. And over there, that blue device there with the white insulated on is part of the switching system, which switches this tower off of the circuit at night when it's not being used, because at night we're using the other two. Design an AM antenna to be any height you want it to be. The problem is going to be in matching your 50 ohm transmission line to that particular impedance. We use quarter wave is convenient because it gives us an impedance that we can easily match to. Quarter wave antenna is on the order of about 30 ohms impedance, and our transmission line is generally 50 ohms, and we can match 50 ohms to 30 ohms with networks like that fairly easily. There are certain wavelengths of towers that are extremely difficult to match to, like a half wave. But anything in between can be matched. This particular tower, which is greater than a quarter wave but less than a half wave, is, instead of giving us a tower impedance of about like 30 ohms, which a quarter wave would be, gives us an impedance of about 122 ohms, which we can match to by the design of again, it's a function of that matching network that we saw inside the building.
Is the 50 ohms the radiation resistance?
The radiation resistance of this antenna is 122 ohms. The radiation resistance of a quarter wave is around 30 ohms. Okay, and the radiation resistance of a 5/8 wave antenna, which is what a lot of antennas are designed around, the 5/8 wave figure, is around 50 ohms, which is real convenient because your transmission line feeds at 50 ohms. So a lot of antennas, even on automobiles that are used even at frequencies that have nothing to do with this, the same impedance principles apply, and they're very close to 50 ohms. Now, to build 5/8 of a wavelength here would be an enormous tower. It would be, well, it would be probably about 800 or 900 feet. Okay, so it's not real practical always at AM frequencies to build 5/8 of a wavelength. It's easier to build a shorter one and to use a matching network matched to it.
So your wavelength depends on the height of your tower?
Right. Wavelength is a function of the function of the frequency. Frequency and wavelength are trade-off of each other. You increase one, you decrease the other. There's probably no I squared R, current squared times resistance. So we calculate, when we trying to calculate 50,000 watts, we know that this tower is 122 ohms of radiation resistance. We know that the antenna current in there is around, well, I can either answer this question or I can let you figure it out as an exercise. We've got 50,000 watts and our antenna resistance is 122 ohms. What is our antenna current?
Stop it right there. They know what to do.
Okay.
We've gone through that, right?
And I can give you the answer later, or you probably figure it out yourself. Let's go down on the right-hand side there. Over on the side diagonally opposite us is a microwave receive antenna, just like the ones that we saw out at Auburn, or similar to that. You can't see it from here. We'd have to go around the other side of the antenna to see it. And that is a receive antenna for the 949 megahertz microwave, which is coming from the studio, and that happens to be one of the transmission lines that's coming down the tower. 70-foot point, then those transmission lines are bonded to the tower. That effectively makes the tower, makes those lines look invisible to the tower. By keeping them insulated from the tower for exactly a quarter wave, the tower thinks that they're not there. In other words, the tower doesn't know that it's grounded, okay, at 680 kilohertz. And that's about, it's not hot like the other one was. It probably has some residual signal that's picking up between the tower and the ground, and what happens is the lightning just jumps across that gap momentarily, and what you in essence have is a momentary ground while it's arcing, and then it extinguishes itself. And of course, once it gets across that gap, now the current is into the ground system, which is the ground radio system. So it has all the space, and it loves it because it's got those ground radials to go dissipate in, and so that actually ends up as a very good ground system for the tower, even though the tower is not physically connected to the ground. Okay. This over here is from the old tower lighting, which is not being used anymore. You have a transmission line that comes in here. These are generally what we call T networks. You can match virtually any impedance to any other impedance using a T network. It's shaped like a T because essentially coming in, what you usually have is we'll have an inductor, and let's see if you can imagine yourself on the top of the T, on the left-hand arm of the top of the T. You come in and you'll have a series inductor, and then on the right-hand top of the T you'll have another inductor, and then from the center of the T down to the bottom, which would be ground, what we call the shunt arm, and the shunt arm will usually have a capacitor, and that's one type of a matching T network. You can see the coils or inductors. It's real apparent there, and then the capacitor, that's a capacitor, and those are capacitors. Now sometimes we'll need a particular value of a capacitor that is just not, you'll end up with some odd value of a capacitor that is not available. There's a couple of ways to get around that. One is by using what we call a vacuum variable capacitor, which is a capacitor where you can actually adjust the capacitance on it, but those are very expensive at these high power levels. The other way that we could do it is by simply putting an inductor in series with it, because an inductor has exactly the opposite impedance characteristic, 3 degrees apart. Now, what happens when you have 3 towers that close together and they all have to have these ground radials is you get to a point where the radials from one tower kind of cross the radials from another tower. Now, what they've done in those particular cases is they put in what's called the transverse strap. In other words, instead of a ground wire, they took a piece of ground strap 2 or 3 inches wide and actually joined they actually stopped the wires at that point. Ran the ground strap, and then the wires from the other tower come and join that ground strap at the same point. So, in effect, what you can see here is these wires right here are not really the full quarter wavelength long. They attach here, and then they continue as the wires for the other tower on the other side of that strap. Same thing here. We have another strap right along here, okay, where those two join. And what did you call that system? It has our microwave receiver in it. And the reason we have the receiver out there as opposed to in here is to keep the line loss down, because if we had to run it all the way inside the building here, we'd have a lot less signal left. So we mount it out there, and then through that cable trough that we saw outside, the audio actually comes into the building on just audio cables. And then it goes into this room, and on the right side over here, on the bottom, the brown unit says Optimod on it. That's our audio processing, which controls our audio levels, keeps the levels and the modulation high enough. Then it comes from there and goes into the unit above it, which is a stereo exciter. We actually operate AM stereo. There's not many AM stereo receivers around, but that is the box that advises our AM stereo. And it also generates the 680 kilohertz signal. We had an exciter last week that we talked about too, which generated about a 10 watt, 7 or 10 watt signal that the rest of the transmitter amplified. The exciter here is a little bit different function. The signal that you get out of that exciter would not be a fully modulated AM signal. The only purpose of that box is to generate the 680 kilohertz signal and to synthesize the stereo, but most of the AM modulation actually occurs in the transmitter. Have you covered amplitude modulation? Yeah. Okay. Well, if you know the difference between frequency modulation and amplitude modulation, what we have inside the transmitter essentially is 2 big amplifiers. We have a big RF amplifier, and we have it raising this to such huge power level that it can modify or modulate the RF signal that's in there, and that's how we get amplitude modulation. That's different from the FM signal we talked about last week, where at a very low level stage, frequency modulation occurs, and you have a complete composite FM signal all ready to go, and all it needs to be done is amplified. Well, that's different. It's different than here, because when the signal comes into this transmitter, it really hasn't been modulated yet. And when it comes out of here, it has been modulated. So it's got audio stages in here, and it has RF stages, and the amplitude modulation process, which gives us our finished signal. The only door in this transmitter that I can open without it going off the air is this one, which is basically just our control panel. We've got more tubes in this than we do in the FM transmitter. We have, all right, let's talk about the RF stage in here first. The tube over here on the left, the last tube, is what we call a 4-400. It's a Petro, yeah, that is a Petro tube. We have a lower level, solid state, lower level signal, and I can't quote you the watts in this particular case like I can with the FM, because the FM transmitter is a little bit more modular, and I can't quote the exact power levels. I would say the solid state section on here is probably giving us about somewhere around 100 watts maybe. And then it goes into that tube, which may give us maybe 300 or 400 watts. And then it'll go into one of these large tubes over here, which is what gives us our carrier signal of 50,000 watts. Okay, now that's it for the RF stage. Now the audio stage, there's another tube over here. Even though you see two tubes that look identical, they have completely different functions. The one over here is an RF tube, the one over here is an audio tube. It's essentially increasing the RF voltage. Then that is driving what we have here. What we call these two tubes in the middle are modulators. Okay, they provide the last stage of audio amplification before it is mixed with into the RF modulator stage. So what we have over here, because of the fact that an FM signal is a constant, is at a constant power level all the time. It happens, the transmitter is putting out 31,000 watts, it's 31,000 watts. Whereas we're changing the amplitude of the AM signal all the time, so the instantaneous power at any given time is different. Now, when we say we're 50,000 watts, we're 50,000 watts unmodulated. The peak power, when we're modulating 100%, is actually 1.5 times that. So it would be about 75,000 watts peak when we're modulating at 100%. Now, where that extra power comes from in this particular transmitter design is from the second tube over here. We have a carrier tube and a peak tube. And they are both RF stages. But what happens is, without getting too deep into this, is that the modulator tubes drive the peak tube, and then the peak tube essentially adds or subtracts RF voltage from the carrier tube. When it adds at 100%, in other words, it's adding another 25 kilowatts, you might say. We've got 50 kilowatts unmodulated, but we've got 75 kilowatts when it's modulated 100%. But of course, for every positive excursion of the modulating waveform, there's also a negative excursion of the waveform. So there's also a corresponding instant, exactly half wave later, when the carrier actually pinches off to close to zero. There's actually no carrier radiation. So we have positive and negative modulation on AM. During the positive cycle of the wave, the AM envelope gets larger, increases to 75 dY. Okay, if you wanted to look up and learn out more about how that works. Now the Doherty amplifier is different from what we call conventional high-level plate modulation, which is the other transmitter I'm going to show you here in a minute. Any questions about this transmitter? We read these.
And the cyclone glass feeders.
It's a very old scope. In fact, it's a
practically new.
Tube.
And a small typewriter or computer table on rollers.
So if he's not talking, there's no modulation at all,
Well,
right?
we'll see that in a second.
782-2778.
Warms up.
782-2778 in Raleigh.
That's right.
Thank you. Good morning. You're on the flea market?
Good morning. I'm looking for something unusual. I need a December 7th, 1991 copy of the News and Observer. I will pay specifically for it.
Have you called the News and Observer?
Yeah, they can let me research it, but they don't have any original copies. I can, they have, I can make prints of it, but I can't take a whole paper.
Oh, I see.
And my phone number is 782-8961. That's my son was born. My wife wants a copy of the paper.
Oh, December 7th, 1991?
The 1991, yeah, last December 7th. Pearl Harbor Day. Yes, sir. All right. Thank you, Mr.
Thank you. I was going to say that we lost him there. Okay, fine. Good morning. You're on the flea market.
That scope is going to come on eventually. This actually allows us to switch from day to night here, which I'm not going to do because back in the studio they'll wonder what's going on when they hear the thing go off in a second. So I won't bother switching. And then of course there's a time clock which controls when that occurs. This up here is a phase monitor. And this is what we use to determine whether or not at night, when we're using our two nighttime towers, whether or not our currents and our phase relationship between those two towers are giving us the correct directional antenna pattern. This particular phase monitor is capable of reading 3 towers. The third tower, which is the tower that we're using now during the day, it's reading the current in here, and the phase angle reading over here has no meaning at all because there's no phase associated with a single tower. When this thing goes into night mode, we can push tower 1 and night, and we'll read a current over here, and we'll read a phase angle here, and then we'll push 2, and we'll read a current over here and a phase angle over here, and we have licensed values that we have to maintain. We have to have a certain amount of current. The current ratio between those two towers affects the shape of that pattern and where the nulls are going to be. Actually, there are 3 things that will affect the shape of the pattern: the current ratio, the phase, and the spacing of the towers. Spacing and orientation of the towers. All of those 3 things determine exactly what the pattern is going to be. Now, we can't change the spacing and orientation of the towers. That's a fixed constant that we have.
That was designed.
That's part of the initial design. We can, however, vary. The phase between the two and the current ratio between those two towers. And the way that we control that is over here is what we call a phaser. Okay. And what this does is it takes the output of the transmitter and runs it through what we call a power divider, so that it will divide the power, run some of it into the south tower, some of it into the north tower, and we can adjust how much of each. What makes this so tricky is that through all of this, every time we adjust something, we still have to maintain our 50 ohms to match into the transmission line. So sometimes it's a little bit more complicated than it might otherwise sound. And that's what the purpose of this device is this over here allows us to maintain 50 ohms. It tells us what our impedance is going into the transmission line. This will not tell us our antenna resistance out there. We'd have to measure that out there. But this will tell us what our impedance is going into the transmission line. So we read an antenna current on each of the towers, and we read a phase, and if it ever varies at all, we can make adjustments over here. These adjustments really haven't happened. This is call it conventional high-level plate modulated transmitter. We've got 2 RF power amplifier tubes over here and 2 audio frequency modulator tubes over here. The main difference between that transmitter and this transmitter design is this one uses what's called a modulation transformer. And what the modulation transformer does, everybody knows what a transformer is the high-level audio, after it's been amplified by the modulators, passes through a transformer, and the voltage that's developed on the secondary of that modulation transformer then varies the amount of plate voltage on the RF or power amplifier tubes. And by varying the plate voltage on those tubes, it's actually varying the current that's passing through them, and it's creating a modulated envelope. But it's a different modulation. The end result is the same. We end up with an amplitude modulated signal. You can't tell looking at the signal on an oscilloscope or off the air that one is plate modulated and the other one uses a Doherty amplifier. They're just different designs and approaches to getting to the same end. I mean, this is like owning an automobile that's 20 years old and it's got 50